Welcome everybody to the third talk today in Barcelona. Before we start, some organizational things to announce. After this talk, there will be lunch. Everybody from this meeting is supposed to go to lunch at the Greenhouse restaurant, which you can find by just going down the stairs opposite of this room. And yeah, now let me introduce our speakers who come from the WARR Exploration Group, which is a subgroup of the Wissenschaftliche Arbeitsgemeinschaft für Raketentechnik und Raumfahrt at the TU in Munich. It's a student group working on space and space exploration, and this particular subgroup is working on a rover that can build habitation on the lunar surface. And I guess we're very curious to hear about that and talk about it. We have two students from the group, both are studying at the Techday University of Munich. They are co-project leads in the WARR Exploration Group. Brendan Mance is currently doing his Bachelor of Science in Management and Technology and another Bachelor of Science in Aerospace Engineering. He has been the lead for chassis and payload engineering for the rover, and has been on the project for 3 years now. And Saifullah Zekar is the lead for command and data handling, which is the software part of the rover, and he's studying electrical and information technology. And yeah, with that, I would give the floor to the speakers. Please ask your questions at the end. We will have a dedicated time as well.
Thank you very much for that wonderful introduction, Olaf. But before we begin with our actual presentation, I'd like to engage in a little thought experiment so that all of you may share in our fantastic dream world, so to speak. Imagine a world where humanity has successfully pushed the boundaries of space exploration beyond the confines of the International Space Station. Imagine a colony on the lunar surface where humans from all over the world work in perfect harmony with cutting-edge technologies to push the boundary of space exploration beyond its current status. Imagine roads, houses, commerce, infrastructure, all of the banal and common aspects of life here on Earth that we take for granted, but hundreds of thousands of kilometers away on the moon. Well, does everybody have a nice picture in the mind yet? Yeah, right, excellent. So then, give us a chance to show you all our version of this fantasy. Okay, here's first one.
Take some seconds from coming from home to here.
There it is. Yes, of course, there's always a bit of delay with the signal being sent to the moon here. So here is an artist's rendering of a little idea from ESA known as the Moon Village, which is exactly what it sounds to be. It is a permanent human settlement on the lunar surface. Now, before such a vision can be realized, of course, there are quite a few open questions that must be answered. Among the chiefest of these questions, of course, is how can structures be assembled in an environment that is completely inhospitable to humans, and where the only resource to be seen for miles on end is useless moon dust? Well, this is where our project comes into play. Hi, my name is Brendan Mance. This is my partner, Zekar, and we are the team leaders of our exploration. Our current project, Project Rebels, hopes to, within the framework of ESA's Moon Village, create useful structures like houses and roads and all the stuff that I mentioned before from otherwise useless moon dust or lunar regolith. But before we go into talking about the details of our system, I'll give the floor over to Saif, and he'll give you all a short history of our team. Saif, take it away.
Thank you, Brendan. WARR die Wissenschaftliche Arbeitsgemeinschaft für Raketentechnik und Raumfahrt. Translated, the Scientific Work Group for Rocketry and Spaceflight was founded in the year 1962 to compensate for the absence of an aerospace faculty at the Technical University of Munich. In its early days, WARR started experimenting with hybrid rocket technology. Came up with this, the first German hybrid rocket to take flight. Today, the WARR consists of a variety of student groups and does not only rocketry, but also satellite technology, space labs, space elevators, and of course, yours truly, WARR exploration. Okay, we have some signal delays from the moon again. Yeah, the WARR exploration team started in the year 2018 with the aim of taking part in the European Rover Challenge. Through our efforts, we came up with the Warthog, sporting its scientific, science equipment. The Warthog was designed to traverse the harsh Martian terrain and collect and store samples. After 2 renditions of the European Rover Challenge, we sat down and thought to ourselves, is this really what we want to be doing? The European Rover Challenge offered a framework for a friendly competition environment, as well as gave students the opportunity to exchange ideas from different universities, from different countries across the world. However, it expected students to tackle a broad spectrum of challenges, all designed, of course, to tackle the harsh Martian surface. But because of this broad spectrum that it wants to tackle, it offers little room for innovation, but instead encourages going with industry standard solution. We, of course, wanted to go the other way. We wanted to do more scientific and research-oriented work. We wanted to innovate our own unique solutions to our unique set of challenges, which is how we discovered the Igluna Challenge. The Igluna Challenge is a lab initiative which aims to support student groups from different universities from ESA member countries to further lunar exploration technology. They provide the framework to design, develop, and test different technologies, all aimed towards exploring the moon. The special thing about Igluna was that they offered us the flexibility to hand-pick our own project, to design our own concept. In a sense, it was less of a student competition because every student team came up with their own unique solution to a certain problem that humans would have on the moon. And this was exactly fitting for our reason. As you can see here, here is our team in Switzerland in the Igluna field campaign at top of Mount Pilatus, running experiments with our rover. This was actually the first opportunity since the corona pandemic hit for us to do a group picture and to actually be able to be together in one place and do our experiments and actually test what we have worked for all this time. And here you can see a bunch of our teammates heating up lunch using our Fresnel lens, but we will get to that later on. Now, to talk to you more about our mission, over to you, Bren.
Thank you very much. So you've heard a little bit about our history.
And you've heard a little bit about exactly what we do. Now, you'll hear why we do it. So, just as a short reminder, just because of how important this picture is to our cause. This, again, is the ESA Moon Village that we would so much like to be a part of. Now, the mission that we got right now came to be from a variety of space exploration buzzwords, so to speak. And I'd like to talk about a few of them in succession right now. So the first of these buzzwords, of course, is the Global Exploration Roadmap. So I'm sure all of you, or many of you, would be familiar with the fact that many space agencies across the world have had interest in colonizing Mars for the past few decades. But in recent years, it's been decided that actually a very important intermediate step would be to first go to the moon and completely test all of our technologies necessary for further exploration on the moon. That's because if we can successfully settle the moon, this validates the possibility of going further to Mars and beyond. So that is why we chose the moon as the site for our hopefully future mission. And this next buzzword is probably the most important because this is entirely what our entire project is based on. If there's one phrase I want you all to know at the end of the day, that would be in situ resource utilization, ISRU for short. Now, NASA gives a very short, concise, elegant definition for this, and that's any hardware or operation that harnesses and utilizes locally sourced materials in order to create products and services for robotic and human exploration. Now, why is this relevant? Because it would increase our mission performance. Think about it. If we can get away with sending less materials on the initial launch of the mission, you cut down on launch costs, you increase the success rate of the mission. Also, there's the fact that with less launches, you can actually, because you can use resources available on the surface, you are actually able to stay there for a longer period of time. So yes, of course, the mission performance would be greatly helped by those two factors. Additionally, you could also increase the sustainability of the mission. Think about recycling landers and whatnot. But also a more palatable example perhaps would be this iconic scene from The Martian, where botanist Mark Watney was able to use local Martian regolith mixed with his own feces and the fecal matter of his crew members to create potatoes for his own sustenance in his harsh survival situation. Now that is a very classic example of in situ resource utilization. Also, it would greatly reduce mission risk because, as I said before, if you launch less, each launch actually carries a great deal of risk associated with it, to the health of the astronauts, to the for the overhead of the space agencies. The goal would be to minimize the number of launches that are conducted in order to make a mission a success. And if we can source resources locally, we don't have to send resources here from Earth to help in the life support or for the construction or whatever applications the astronauts would possibly need on the mission site. And finally, of course, science operations would also be greatly helped because of the greater infrastructure that would be built on a moon village. And now, a short graphical overview of this entire concept of in situ resource utilization. Down the center, you can see the entire production chain of acquisition, prospecting, and then the processing of this acquired material. Then finally, at the very bottom, is what we do, in-space construction and in-space manufacturing. Then, of course, also on the right, you see the very important support systems, for instance, life support, power, storage, and transportation. So, why is ISRU significant for the moon village? Well, the dominant concept right now for any structures to be sent to any prospective moon village would be to first send a plastic pressure vessel up on the initial launch. This pressure vessel, upon landing, would then inflate and serve as the foundation for habitats that would be constructed later. However, this plastic habitat is not sufficient to protect our astronauts from environmental hazards such as micrometeorites or radiation. Therefore, we need to have an extra layer of protection on this pressure vessel here, and this would be the lunar regolith that we'll heap onto this habitat in order to have a little bit of a shield for these astronauts. However, if you were to just pile dust on top of a structure, of course, after time, after a few impacts, all of that will go away and our shield will be rendered useless. Therefore, we need to have some kind of solution of holding it in place. And that's exactly where our structure building comes into play. We turn this regolith into rigid material and for use in this shield. So now you've heard what our mission is. Now let's start to talk about exactly what is under the hood, our system. So our system is an amalgamation of two already existing technologies. On the right, or left, sorry, speaker perspective. The left, you can see a solar sintering platform. This was developed by Markus Kaiser, a freelance artist based in the Sahara Desert, where he converts the sand there into very interesting sand sculptures. So the way this system works is he has a large Fresnel lens right there, that large square optical system, and it gathers sunlight into a very small point at the bottom of that pivot. This point gets extremely hot because all of the energy has been concentrated to that singular point, and you can actually melt some materials with it. And that is the principle of sintering. Once you melt some materials in a powder, you can use these melted materials to stick together the less meltable materials, and you have a solid structure that is a lot more less prone to breaking than glass, but still quite rigid. Then, of course, on the right side, you see the Curiosity rover that we all know and love, the flagship of NASA's Mars exploration campaign. And yes, Curiosity and his brothers are very well developed, and I'm sure we're all very familiar with their innovations. So, now that you've seen what our technologies were combined from, here is LARS, the Lunar Automated Rover for Solar Sintering. As you can see, here you can see that an abbreviated version of the solar sintering apparatus mounted on the very front of the rover, right here. And of course, a rover based on Curiosity and the siblings thereof with its standard rocker bogie suspension arrangement and general structure. So, unfortunately, we can't get him to run today for safety concerns, but we'd like to talk to you about first how this concept came to be. Then we'll go into the technical details about Lars himself, and we'll share some findings from the field campaign that we showed earlier from the Igluna. All right. The first area of conceptualization I would like to talk to you about is in the rover itself, the mechanical part, the driving part. So as you can see there, we tried quite hard to find a new innovative solution that didn't completely just one-to-one copy NASA's design. We have some very radical concepts here on the bottom right, all affectionately named, as you can see. But for one reason or another, they were incapable of fulfilling a mission in any sense of the term. They would fulfill certain requirements very well, but others they would just completely fail on. And we can't have that in a mission setting. Then we have two more conservative designs. We have the standard rocker bogie suspension rover there, the Normie as it's called. Then in our literature review, we found another variant of this that we called the Skater Boy, where the joint between the rocker and the bogie actually has an additional swiveling vertical joint right there to allow for the wheels to all be in different trajectories. This allows the footprint of the rover to be minimized, as each wheel will travel over one particular piece of ground only once, and therefore decrease the destruction on the surface. However, we eventually realized that we won't need to drive over any sintered material that we freshly created anytime in the near future. So we deactivated this requirement. The skater boy was an unnecessary level of complexity that we discarded, and we reverted back to the normie. And a little bit of a treat for you all. Here's a tidbit of information. Back on the concept of minimizing surface deformation, we tried to create a wheel that had that was configurable. So in one configuration, these grousers here would pop up and to maximize traction for the rover. Then in its second configuration, the grousers would fold in and allow for lower surface deformation. So yes, ironically, in our attempt to be innovative, we literally reinvented the wheel. Here is the CAD implementation of our rover. So the main parts here are a chassis, which is a very interestingly shaped chassis, I would like to point out. A bit of an anecdote about this design. Myself and a few of our other mechanical engineers were sitting in a Zoom call trying to come up with a good concept to fulfill our requirements. And we were looking at the various letters on the keyboard, trying to see which of these geometries would actually help us achieve a center of mass that was lower towards the back of the rover, so that when the payload would move forward and backwards, the weight would be offset. Yeah, so the entire idea of modifying the chassis was to make sure that there would be space and proper functioning room for the payload. Our second part here is an abbreviated undercarriage from the rocker bogie suspension arrangement. This again, like said before, it's very similar to the one used by NASA on the Curiosity rover and all its other exploration rovers. And here, instead of those radical wheels that we showed you earlier, we have a more conservative design with interchangeable profiles, so we can manually switch the profile depending on the application that we want to go on at the particular moment. So that's the mechanical design of the rover, but how does it move? Saifullah will now tell you about electronic speed control.
Thank you, Brandon. Why don't you buy your own ESCs? A phrase that we asked ourselves a lot, a phrase that was told to us a lot. So when you imagine a rover, you think of this extraterrestrial electric vehicle with all this high tech driving around these rough surfaces on planets. But in a sense, the hardware that controls the motors, the hardware that drives the rover around, is pretty similar to the hardware that drives our electric vehicles back on Earth. So in a sense, this problem, an electronic speed controller, a motor controller, already has a multitude of industrial solutions that we can go with. But as I mentioned before, we wanted to innovate. And oh boy, innovate we did. This is our electronic speed controller. Small enough and thin enough to fit in your wallet. It is about 9 × 3 centimeters, smaller than a business card. It is capable of driving 2 motors simultaneously, the motor which drives the wheel and the motor which steers it around. For our power stage, we used gallium nitride field effect transistors, which in contrast to traditional MOSFETs found in today's, in the industrial electronic speed controllers, have a much shorter switching time. Now, for those of you in the audience who are not familiar with transistors, don't worry. All that means is those things are as efficient as can get, or at least as we could have gotten them. They are so efficient that the low power logic, which generates the control signals, ends up dissipating more heat than the power stage, which is supposed to handle all that high power those power-hungry motors need. Why did we end up designing our own ESC and not just buying one? That would have been the simpler route. If you take a look at our wheel assembly right here, also in front of you on Lars, you can see that the space that we had for one of those circuit boards is very small. Today's electronic speed controllers do not fit in that tiny space, and not an electronic speed controller that can control 2 motors at once. We also had to work with tight efficiency requirements. Designing something for extraterrestrial application, you have to take a good look into its power consumption and really make sure you don't lose power where you can save it. Moving on to a more broader view over the system. As you can see here, we have 6 wheels on the rover. Each wheel needs to be controlled individually. This means we have 6 of those electronic speed controllers mounted, each of those with its own processing unit to control the wheels. Not only that, but due to the complexity of our system, we have a variety of subsystems, each with their own or a multitude of processing units. What we ended up with is a distributed system of multiple microcontroller units, each of those with its own set of tasks, with its own set of data. We had to make sure that all of those microcontroller units, all of those subsystems, are also able to communicate and synchronize with each other if we are able to do a mission. This distributed system also had to be remotely controllable. Once you send something on the moon, you can't expect astronauts there to be driving it around. It has to be automated, it has to be remotely controllable. For the former of the problems, we came up with this solution. RODOS, a real-time operating system developed originally by the DLR, the German Aerospace Center, to exactly tackle this problem: communication between microcontrollers on a distributed system. This real-time operating system implements a publisher-subscriber system. What does that mean? It means those microcontrollers, those processing units, the single subsystems really don't have to be aware of the state of the other subsystems. Each subsystem is able to publish data, commands, or subscribe to it. It doesn't really matter who is doing. They are always able to reach each other. We have another layer of abstraction on top of that, which is called DOSes, developed by our sister team, the satellite technology team, which further abstracts the participants in a distributed system, and therefore making it really not important where what piece of software is, where what piece of software which handles what sensor or which does whatever task. As long as it's on the system, it is able to be communicated to be commanded, and we can harvest data from it. It's as simple as that. Here we have the solution to the latter of the two problems, the remote operability. What we have made here is a web interface that we named the WARR, of course. And we have a short video demonstration here. The observatory offers different tabs to be able to operate and monitor the rover. Once an operator connects, he can choose from a list of different sensor data, which is all transmitted and viewed in real time to the operators. Operators are also able to send an instruction or a set of instructions to the rover to be executed. Those instructions, as I explained before with our software, end up finding their goal and being executed. Here we have a series of G-code transmitted to our payload, and voila, it moves around. It's as beautiful as that. This web application was designed with the idea of multiple operators in mind. This means all you need is a laptop and a solid connection. You're able to connect to the rover, monitor whichever part you want, command whichever part you want. Now, with all those electrical consumers and all those power, all those processing units on the rover, we need somehow to be able to deliver power to all of them. And as I mentioned before, they should all be able to communicate and synchronize with each other. So there has to be some data bus to enable that. Now, we can go with a traditional approach, of course, and design a cable harness, which really does not look appetizing, is very complicated to plan, requires real extensive planning, and once you decide, oh, I need to make a slight change, you need to dismount the entire thing and rebuild it again. So this approach was not very versatile for us. We had to innovate once more and come up with our own solution to this problem. Ladies and gentlemen, I present to you the power terminal, a circuit board with a set of standardized connectors working on the plug and play concept. This terminal, with its 8 pins, is able to provide power as well as access to the shared CAN bus to all of the electrical consumers. Once we have an extra consumer, an extra circuit board, a new processing unit, a new challenge, a new task, you just plug it in. No new cable harness, no stress, nothing. It's as clean as that. Now, of course, our power distribution system consisted of 3 of those power terminals located in the center and at the sides of each rover, all connected together. We would power the rover using a lithium iron phosphate battery. And we also designed our own battery monitoring and observing system to be able to calculate power consumption by the system and also to make sure that it stays in the safe parameters. And now we have another short video of some production and testing that we did. This is the manufacturing of our ESCs. Some of the components that we used on them were really small that we really had to work with microscopes to be able to manufacture those. Here we have some software testing for our battery observation system and monitoring. And here we have some testing and implementing of the software which drives our motors. And yeah, those were good times, stressful times at some point, but in the end of the day, here we are. Now, moving on to the interesting part of the rover, the payload, the part you've all been waiting for. Brandon, take it over.
All right. Well, you may probably be asking why exactly we decided for solar sintering. So let's quickly go to an overview of all the different options that we had for our sintering application. So for additive manufacturing, in the context of in situ resource utilization, we can go with binder using processes. But for this process to work, you would need large quantities of binder that you would bring with you on the initial launch. And of course, that sort of defeats the entire purpose behind in situ resource utilization. So we decided against that in favor of non-binder powder bed fusion technologies. And of these, there are 3 that we have considered. First, we have microwave sintering, which is capable of sintering large areas all in one go. Unfortunately, this method only works for real, authentic regolith sourced from outer space because they have nanoparticulate iron particles that really can't be replicated in a lab here on Earth. So no simulant can actually replicate those qualities. So we decided against microwave sintering. The next two, laser and solar sintering, are very similar in that they both use very high energy light to heat up selective parts of the powder bed. Laser sintering, however, requires a large amount of power. And in a mission environment, we expect the power that can be supplied to be not unlimited, so let's put it that way, unless NASA decides to build a nuclear power plant up there or something like that. Yeah, so we decided, oh, and also because we are a student team, we don't have the access to the essential laboratories and equipment and the know-how to actually work with high-powered lasers for sintering. That's why we decided for the slightly less reliable, but still very easily accessible solar sintering method. Now we have a few concepts of our payload that we explored because, yeah, there was almost very limited work on this, so we were free to conceptualize all we'd like. But among all of these concepts, there's a few things that tie them all together. First of all, we need to have some kind of apparatus to gather the incoming sunlight. So we decided either for a Fresnel lens or a parabolic mirror. In the end, we decided for the Fresnel lens. Next, we needed some way to move the lens in a way that the incoming sunlight can be properly focused for solar tracking. And we had a bunch of concepts, moving the lens on some rails, moving the rover itself, which obviously is not a very effective method of that. And eventually we decided on a concept where the lens would be moved in elevation and azimuth directions in order to properly track sunlight. Then finally, of course, we needed some way to move that concentrated beam of light on the ground so as to 3D print something effectively. And to show exactly what we came up with, again, this is another CAD implementation of our payload integrated onto the rover. So first, we have this lens and shutter assembly, the LSA for short, that houses our circular Fresnel lens. And this would collect the sunlight, as explained earlier. Then this lens and shutter assembly would be moved by an arc assembly in the azimuth and elevation directions in order to track the sun. Then as soon as the sun has been effectively tracked and a beam has been created, we have a gantry that can move the entire beam in X and Y directions in order to properly sinter material on the ground. Granted, because we only have two axes of motion for our gantry, we could only generate two-dimensional structures because, yeah, we're taking baby steps towards the greater goal of being able to make 3D structures. And here, finally, some findings from the field campaign. Yes, the entire system worked, but unfortunately, there are a few problems that we have discovered during testing. First and foremost, when we did a risk analysis very early on in the development process, we underestimated the criticality of having good weather. Like, we expected there to be 80% of the days on a hot summer July at the top of a mountain to have almost clear skies and perfect sunshine. Unfortunately, that didn't happen. It was all cloudy, and yeah, that did not work out in our favor. Also, while we were sintering, we discovered that the solar tracking was a little bit too sensitive to be particularly effective. Every minor disturbance, every cloud that would come into view, any person walking on the side would kind of disrupt the solar tracking and confuse the entire system, make the focus spot out of focus. Then also we had we discovered that the payload was missing a degree of freedom. We needed an additional up and down motion in order to increase or decrease the spot size that was generated by our lens, to make sure that we always have an even sintering energy down at the ground surface. And you can see here, these are the 2D structures that we have sintered with our apparatus. They're not as even because of the reasons I mentioned earlier, but the concept does work. Finally, we'd like to talk a little bit about our vision for the future. Saif, take it away.
Thank you. So, from our experiments at the Igluna field campaign, we came across a lot of problems that were overseen during the design phase. One major problem was, as my colleague mentioned, electronic safety. A lot of electronics had to be sacrificed to build this guy right here. So it is a factor that really needs to be looked at from our side. There is also a lot of software issues that we had. I was talking before about how beautiful our software is, huh? But yeah, software has to be robusticized, it has to be able to react to a lot of problems that we could not have foreseen during our design phase. However, now that we are aware of this, our goal is to further robusticize our system, to perfect it, to make it reach the point as we have envisioned it before. For the near-term future, we are looking into taking the sintering concept into the third dimension. As we are right now, we only sinter two-dimensional geometries. Now, of course, how this would work, it would need to be a layer by layer sintering concept in a sense. And yeah, we are also looking into using doped simulants, as in simulants mixed with other materials. One suggestion from our industrial partner, Orbit Recycling, was to use a mixture of regolith and aluminium. So to actually melt the aluminium and use that to bind the regolith together. There is also the opportunity to harvest the gaseous byproducts of the sintering process, such as oxygen gas, which would be a valuable resource on the moon. Our technology is still in its early days. It needs to be matured, possibly through terrestrial applications, before considering lunar application. We are a group of students with the aim of further developing lunar exploration technology. As children, we used to be fascinated by magnifying glasses. Go outside on a sunny day, focus the sunlight and use it to burn up a sheet of paper. Some people used ant colonies for that. From a child's curiosity and a knack for experimentation, this concept was born, concept of solar sintering. Ladies and gentlemen, we are WARR Exploration. Thank you so much for listening.
Before we do the question and answer, I'd like to thank our sponsors here. Your support has been very valuable for us. We couldn't have done it without you, and we hope for your continued support in the future for our future endeavors.
Special thank you to TNG, of course, for this opportunity. We have enjoyed our stay here.
Most certainly.
Yeah, thank you for this very interesting talk. We are all looking forward to living on the moon. We have at least 10 or maybe 12 minutes for questions. Any questions from the audience?
Okay, thank you for the talk. It's very fascinating what you're building here. The boards that you designed, are they already radiation hardened or radiation tolerant, or is this still terrestrial stuff?
You are referring to these squares that we...
The motor controllers.
Oh, the motor controllers. No.
Well, everything on the system as it is built for terrestrial applications. So this is still in its early stage, and we have decided to focus more on the proof of concept of solar sintering. So nothing is radiation hardened as it is. Yeah, but that's a near future step to take, of course.
So my question is similar direction. So if I see optical parts together with a sand area, that seems that the Fresnel lens will not live very long. So did you consider that, or how much larger is your current Sentinel lens than you would need to generate power? So how much dust can you live with on the surface?
So like we said before, we haven't really considered our proof of concept in a space environment yet. We're still trying to develop it on the Earth, and we did start to consider dust mitigation strategies, particularly this shutter here that can fold itself and reveal the lens. But that's obviously a very low-level solution at the moment. We need to investigate more sophisticated dust mitigation technologies in the distant future.
Okay, we have a few questions from remote participants. One question is, I can imagine the sun's radiation intensity is much higher than on the Earth's surface. So the system makes a lot of sense there, I guess. Can you say what's roughly a factor, how much stronger the intensity is on the moon's surface? Or even better, what's the power in watts that you expect?
Ooh, this is unfortunately a little bit of a question for our payload specialist, who unfortunately couldn't be here today. But what I can say is the temperatures that we reach with our current setup, they are, if I remember correctly, it's about 900 degrees Celsius. Is that correct? Yeah, 900 degrees Celsius. This currently is suitable for our application in melting a soda and quartz sand mixture, and sintering that. That's what these were generated from. And we also tried a little bit of our luck with legitimate simulants that were given to us by the chair at our university. These were a little bit more temperamental to work with because for reasons that we haven't yet fully explored. But like we said, we will explore that earliest in the next year.
Thank you. How does sintering in low G in a vacuum compare with testing on Earth?
So again, this is another question about our very far distant future space application, and we really have not considered these at the moment.
So that's the reason that we decided to use CAN-bus technology to communicate instead of actually using a modern network gigabit connection.
Well, I think this is a question for also our electronics specialist, but the reasoning behind using the CAN-bus is its versatility. All you need is 2 cables unrouted around the entire system. It's simple, it's easy to use, and for a fact, with the real-time operating system that we use, the CAN-bus was actually the standard mode of communication between our microcontroller units. CAN-bus is also readily available on most microcontroller units that you can buy today, and yeah, it was sort of the beginning. I hope this answers your question.
How long did it take to produce these little squares that we can see here?
Oh, a matter of minutes, actually.
Mm-hmm.
Yeah. Yeah, let me see if we actually have I think we have oh no, unfortunately, we do not have a video of the real time of this structure generation, but you can barely actually see the focal spot moving in this video. It's a really slow process, so it takes a few minutes actually just to make this little tiny few centimeter by few centimeter square.
It's 30 millimeters, yeah.
One more question about sintering from Andreas Zoller. During your tests, are you sintering artificial lunar sand, or how do you test that it will work with the actual lunar material?
So I answered this a little bit in the previous question. We used for this a quartz sand and soda mixture, and the flux material was the soda. That was the easily meltable material that could bind the harder to melt sand particles together. And again, in about a year, we expect to be able to work with legitimate lunar simulants, such as a lot of backup slides, sorry. Such as these right here. So yeah, we actually were able to generate a little ball of sintered simulant, but unfortunately this actually just completely melted. This is a glass ball and not actually legitimate sintering. We can't have that for, we can't make a house out of glass or a radiation shield out of glass because yeah, glass will shatter. So yeah, we're trying to work out the bugs onto exactly why simulants are more temperamental than our mixture, but this is work for another year.
One more question in the same area, probably. The centering, what's the resolution you can get, and how is the error?
So I believe we are able to achieve focal spot diameters of 2 centimeters, 2 to 3 centimeters. Unfortunately, I can't give a exact number as to just how much resolution we can get with that spot, but yeah, all I can say is that the spot is about 20 to 30 millimeters.
Okay, do we have any more questions? Of course.
I don't need to ask a question, but yeah. My question is, do you somehow track the sintering itself? Because what I would expect if you have rough surfaces, you already said that you need a third dimension, that the focal spot will not hit the spot where the ground is.
Right.
And have you put any thought into how to actually tackle this?
Yeah, so actually we do have a camera mounted here in our sintering. You can't really see it behind this shutter assembly, but there is a camera down there. We haven't implemented any kind of vision or distance monitoring with this camera, but we expect to be able to use that in conjunction with the additional z-axis degree of freedom that we'll add in the next iteration to be able to direct to change the size of the focal spot depending on how far it is from the ground.
Okay, thanks. So when you talk about your next edition of this vehicle, I assume that a whole bunch of problems could be solved with extending the size of the vehicle, right? So when it comes to the time that is needed to sinter material and also the maximum heat that you can reach, did you plan for a bigger vehicle as well? I mean, there's on the other hand a trade-off with which size of vehicle you can send to the moon, right?
Yeah, this is actually one thing that we had to cut for time in our presentation, but I'm glad you asked this question. The scalability of our rover was a question that we have been struggling with very early on, because we were envisioning either really small rovers that would drive on freshly sintered surfaces and then just build them up layer by layer. But then we also had an alternative concept of a gigantic rover with like a crane arm or something similar that can sinter very large portions of a habitat just by standing in one place, and then it would move to another place to generate the next part of the habitat. So we don't have a concrete answer as to exactly how we're going to scale the rover, but this is something that we will work on in the distant future. For the next year, we're just going to make LARS a lot more robust.
More questions? No. Okay, we have time.
Sorry. Okay.
Last one from me. When you sinter the materials, do you sinter them at the place where you need it, or do you just use like kind of a football field, sinter there, and then pile it up somewhere else?
No, we sinter them where we need them.
Yeah.
Yeah. So we had a test sandbox, and yeah, we just sintered directly on the ground.
Yeah, the approach that we're going towards is not something like to sinter bricks or some intermediate material which can be used, but to actually sinter the structure on spot directly there where it shall be used.
Okay, I think we're through with questions now. Of course, you can address the speakers right now. I would like to thank you very much for your very interesting talk, and it's always nice to see some hardware.
Oh man.
We have a little bit of thank you.
Thank you very much.
Thank you so much.
Yeah, and to the audience, I hope you enjoyed this talk and enjoy the rest of the day. As a reminder, all of us in this room are supposed to go to lunch at the Greenhouse restaurant, which you should find by just going down the stairs opposite from this room. So, thank you. And thank you again to the speakers.